Welcome back, class. Tonight we're going to learn about work and how work relates to energy. And thus far we've been learning about potential and kinetic energy. And we know how to calculate potential energy, we know how to calculate kinetic energy. We know that when an object falls, for example a roller coaster, that the amount of energy the roller coaster has is conserved so long as no work is being done. So now we really need to understand what work is. So work is defined as the product of force and displacement that changes the energy of an object. So remember, product is multiplication. So here we see the force times the displacement will change the energy of an object. Okay? And so we can calculate the work done by either multiplying the force in newtons times the distance in meters that force is applied, or by calculating how much the energy of the object changes. So if the kinetic energy is increasing, because the velocity is increasing, if we can calculate how much that kinetic energy increases, we know exactly how much work was done. So let's look at a simple case. A 50 Newton force is applied to a box, and the box is pushed horizontally a distance of 5 meters while that force is applied. And if we ignore air resistance and friction, then we can intuitively understand that this box is going to accelerate, it's going to speed up, and it's going to end up at the end of the 5 meters with a certain amount of velocity. And as a result of that, have what type of energy? Yes, it's going to have kinetic energy. So this box has increased its kinetic energy because we've applied this force to it. How much work was done? Well, we can apply this formula here, force, 50 newtons, times the displacement of which that force was applied, 5 meters. And we get 250 joules. That would be exactly equal to how much kinetic energy this box gains through this distance. So again, ignoring air resistance and friction, this box at the end of the 5 meters will be traveling a certain speed because we've given it kinetic energy. Other examples of doing work. So remember, work always changes the energy by an equal amount. These first two examples, lifting a box and climbing stairs or a ladder, these two examples involve changing what kind of energy? We're lifting an object vertically. That's right, it involves changing potential energy. So we can calculate the work done by lifting a box or climbing stairs or a ladder by either knowing the force that's applied times the vertical distance, or by calculating the change in potential energy. These last examples here are all examples of work that changes kinetic energy. Here, brakes stopping a car. Well, the car had kinetic energy, and it's reducing the kinetic energy and stopping it to nothing. So that work would be done to reduce the kinetic energy of the car. It's changing it. Friction and air resistance can also do work. A lot of times we ignore them, but sometimes we don't. And so when we're not ignoring air resistance or neglecting it in friction, those forces would reduce the kinetic energy of an object. You would have to apply more force to make up for that. We've talked about that. And then an engine accelerating a car. When you accelerate from a stoplight, the engine is applying a force to a distance that's increasing the kinetic energy of a car. So these last three examples were all examples of work that increases or decreases the kinetic energy. It changes the kinetic energy. So what are the units of work? Well, it turns out they're the same as a unit for energy. It's a unit of force, which is a newton, times a unit of displacement, which is a meter, a newton meter. Now, maybe you don't really see how this equals a joule, so let's look deeper. What is a newton? Well, it's a unit of force, which is a unit of mass, times a unit of acceleration, from Newton's second law. So we have a unit of kilogram times a unit of acceleration, meters per second squared. And so that's a unit that's equal to a newton, and we multiply that by a meter. So this becomes a kilogram meter squared per second squared. And we already know from yesterday's lecture that that is equal to a joule. So let's go ahead and look at this example here of a child on a swing again. So what I've done is focused a little bit more so you can see the diagram. So we have a 25 kilogram child on a swing, and the child is raised from the ground to a height of about 1 meter. So here you can see the child raised to a height of 1 meter. Now, we don't know what force the adult applied and we don't know the distance the adult applied the force, because the force is being applied in this direction, and the distance is a semicircular arc. We don't know the distance. So you might think, well, we can't calculate the work done. But actually that's not true, because recall that work done can be calculated by force times the distance through which the force is applied, or by calculating the change in energy. Now, what kind of energy will we change about this child? We're lifting the child vertically, holding him or her in place. That's right, we're going to change the potential energy. So we're going to increase the potential energy of the child by lifting the child vertically this 1 meter. So we can calculate the work done even though we don't know the force and we don't know that total distance we lifted the child, because we applied that force through this semicircular distance. We don't know that. But we do know how much energy we gave the child. So we're going to calculate the work done by calculating the change in potential energy. Remember, change means final minus initial. So we have the potential energy final minus the potential energy initial. Well, at the bottom of the swing, before we lifted the child had 0 potential energy. So we can calculate the work done by simply finding the final potential energy of the child by multiplying the mass of the child times the acceleration due to gravity times the height. And when we do that, we take 25 kilograms, we multiply it by 9.8 meters per second each second, and then we multiply it by the height we lifted the child, 1 meter. And we get, if you plug it in your calculator, 245 joules. So that is how much potential energy we gave the child, and that is exactly how much work was done to lift the child there. It doesn't matter the path. You could lift the child vertically, just lifting it straight up. You could lift a child along this arcing swing like we did on the swing set. But as long as the child ends up at the same height and started at the same height, we're going to change the energy by the same amount regardless of the path we get there. Therefore, the work done is the same regardless of the path. So this is a little bit about work and about how work changes the energy of an object. And tomorrow we're going to apply this a little bit more. What you need to remember is that anytime we're doing work, we're changing the energy of an object. And we can calculate that in 2 different ways, by either multiplying the force times the distance, or by finding the change in energy, the final energy minus the initial energy. Either way, you can calculate the work done. Have a great evening. I'll see you tomorrow.